homework. It's something I don't have homework to tonight. It's just I don't like do the homework that's due later it's due tonight.
Do with the days I do not but I do.
I'll be done about 6.
Sorry. Say different. No worries. Do it.
I wish. I wouldn't be able to go to the range until like.
Let me fix this. Just tap it, make sure it's working. Alright.
My computer just has a week of battery.
I know it goes.
Okay, so Colt Carroll's here. Colt Carroll, come on. Howie and okay. All right, I had a question. Somebody asked me. Does it work? About I think it's from 323. Is that one? Which one? Is that? I'm going to do this, but I want to do it two ways. Before I just put in the values they use. Yes. Can you hear me?
Yep.
I'm going to first do that problem, and I want to tell you where we're going today. I'm going to try to do the standard problems of line charge, loop of charge, plate of charge, and then infinite surface, so you'll have those down. Then hopefully we'll move into Gauss's law. And the reason I want to really get to Gauss's law is because Gauss's law makes all this easy. All right, if there's high degrees of symmetry, it's very easy to do this stuff. But you still need to do it from a differential perspective. So, first, let me give you a review before I get going. First, if you have an infinite line charge, just with the charge density rho L, and this is infinite, and your distance rho away, you remember that the electric field from this would be radially away from this, so I'm going to call it just E rho. And the magnitude would be the line charge density over 2 pi epsilon naught over rho A rho. Y'all remember this? A rho was a vector pointing away from the center of that line, or the shortest distance to that line was from the point of observation. And that doesn't have to be just A rho in the sense of the cylindrical system. Y'all remember we doing some Friday class? It's very important to appreciate that. Now, that's in the line of charge. If we have a ring of charge, and the ring of charge, I'm going to do this. You can call this X, Y, and Z. And if you have a loop of charge as such, and the radius is rho, we're using rho for a reason. Now, this is a ring of charge centered on the XY, it's centered on the Z axis, it's in the XY plane. Y'all follow me, class? And if you're at a height Z above here, you'll use H in the book. And you go ahead and you find, remember I talked about this distance here would be R, and that distance is actually equal to the square root of rho squared plus Z squared. We've done this problem, so I'm not going to redo the whole problem, but you would get an electric field here that was proportional to rho L. This is assuming a loop with a charge density rho, or a line charge density of rho L. Do y'all remember this class? This problem, how many do? All right, this is very important that you try to keep up with this because it gets very confusing quickly if you don't. So it's going to be proportional rho L. It's inversely proportional to 2 epsilon naught, right? Then it's multiplied by both Z and rho. It's in the AZ direction. Now in his book, he'll use H and he'll use A for the radius, but these are just symbols. Then it's divided by rho squared plus z squared to the 3/2 power. And that would be in volts per meter. It's in the z direction. Y'all remember me doing this, right? Class? Okay. Now we're going to use, and I always call it the building block approach. We're going to use this right here. And we're going to say instead of having a line charge density of rho L, we're going to have a density that's going to have, we're going to make this wire kind of fat, if you will. We're going to give it some thickness, the differential thickness, E rho. And then we're going to find the charge on that differential thickness and replace rho L with, we're going to say that rho L is actually going to be equal to rho S times d rho. Now let me put it here. Rho L will become rho S d rho. Now if you think about it, rho L has the units of charge per meter. Rho S is charge per meter squared, but d rho has got the units of meters, right? So the units work out. You all follow me on this, class? How many understand this? This is a differential approach. So now come over here. I'll do the problem with the values they had, but I want to do this with a charge density that's constant. So now assume you have a plate down here. And now the plate is going to have a radius A. Alright. It's going to have a constant charge density here of rho S. So really you have a surface here, a charge, but we want to know the electric field on the z-axis. So I'm going to come up a point z away, and I'm going to calculate that field. And the way we do it, or the easiest way to do this, instead of just writing a differential electric field from a differential surface charge, we're going to take a ring of charge and make it differentially thick. Y'all follow me? So when we do this, I'm going to come out a distance rho away, and now I'm going to go ahead and say, now I have a loop here that's got a thickness or a width of d rho. And I'm going to find the differential electric field. I already know what it is from this loop right here. I'm going to get the differential electric field in the z direction. Then, once I have that, I'll find the total electric field by integrating that value over the range where the charge exists. Does this make sense? The logic is very clear if you think about it. So now I take this and I say that dEz is equal to, everything's the same except rho L is replaced by this, and I'm assuming the surface charge density is constant. So it's equal to rho, and I'll put the integral here, rho S right here, and now that's going to be times d rho. Then it's times z rho, and then you have az. It's over 2 epsilon naught. And here it's going to be z squared plus rho squared to the 3/2 power. And I might as well get rid of this differential. Now I'm talking about the actual electric field at this point. And EZ would be this differential electric field integrated from rho equals 0 to rho equals A. Everybody follow the method? The only thing I've done is replaced rho L with rho S times d rho. You all follow me, class? But now it becomes a differential when we have to do the integration. Y'all follow me? All right? I think this might be in the book, but what?
Should there be a pi at the bottom? Like 2 pi either way?
Do you have your book? Can anybody go ahead and check that? The pi integrates out when we do the integration around a circle. Do you remember doing that? How many remember this one? Right? The pi goes away because we're going to integrate from 0 to 2 pi. Y'all remember that, class? There's normally a 4 pi underneath. When we integrate from 0 to 2 pi, we're left with 1 over 2. Can you, is it in the book? Where's the loop in the book? Anybody have a book to take a look at? I'll give you a page number. I'll take the rest. That's a good question.
It's not with the other.
What?
It's not with the other.
What did you say?
He said it's not with the other equation, so he's taking a little bit longer to find.
Oh, all right. Just look for the loop. It's in, I forgot where it's, ring of charge or something like that. Yeah,
It's on page 138.
page 138. All right, now, at this point, we have to do the integration. Let me just show you something. This is the way I do it. Now, I'm not going to ask you to do crazy difficult intervals. All right, this is not a class in solving ridiculous intervals. All right, you can look it up on what, Wolfram Alpha or tables, or, I mean, you can do this any which way. This is an easy one. So if I look at this, easy for this one, first I take all the constants out, so I take rho s out in front. Then I take z. Remember, z is a constant where it's given height and weight, that height above there. Then I take 2 epsilon naught out front. Now, let's see what else I have. Now I got to put the integration in here, so I have to integrate this from rho equals 0 to rho equals a. And now I have, it's in the az direction, I'll take that out front. So I have rho over rho squared plus z squared to the 3/2 power d rho. This integration isn't bad at all, but you all follow me on this? I'm just, again, I'm pulling out everything that doesn't vary with rho, and then I'm going to do the integration. I'll put it right here. So when you look at this one, you'll see something that's pretty obvious. Here, the form of that integral is what? The integral of, you can say it's x over x squared plus a squared to the 3/2 power dx, right? And you look at this, I can actually put it this way, I can put rho in. I'm used to doing it the other way, but rho d rho, and then put in rho squared plus z squared. Now, if you do this one, and here rho equals 0 to rho equal a, if you let rho squared plus z squared equal u squared, then you can see 2u du equals 2 rho d rho, right? If you do the differential, the 2's go away. Then you can turn this integral into something fairly straightforward. You can say, now that's the integral of u du. And then downstairs it becomes u squared to the 3/2 power. And here it's going to, instead of rho goes from 0, u itself would go, look at this, u is positive is going to be rho squared plus z squared. So when rho goes to 0, u goes to z. Y'all follow me? It's rho 0. So it goes from z to, and then the upper part is going to be the square root of a squared plus z squared. And that's u. Now, if you look at this integration, just look at this. This is what? U over u cubed. Y'all follow me? I mean, it's actually going to be, what happens is you're going to get u squared to the 3/2 is u cubed. So it's really 1 over u squared. Do y'all agree with that, class? Integrate that, you get minus 1 over u, right? And then you evaluate this from u equals z to u equals square root of a squared plus z squared. And that means when you evaluate, since it's a minus sign, you can change the upper and lower limits to a plus. So it means it's just 1 over z minus the top one. Do y'all follow me, class? So here it becomes easy, and I'll put it here. But this is an important point I'm about to make. So now I have rho s z a z over 2 epsilon naught. And then this whole, all this business becomes 1 over z minus 1 over square root of a squared plus z squared. Now this is a relatively straightforward integral. It's easy to do because it works nice, right? It comes out really nice. What do you notice about this? If you take z through here, you know, follow me, this is a straightforward thing. It probably is in his book, but I would go. I multiply z through there, and what happens? Well, now I get this 1 minus, and this becomes z over that, and that is the answer for EZ on the z-axis for any kind of a circular dish with a constant charge density. But here's the next step for this. Do y'all agree with this, class? The thing people always want to know is, well, what is the electric field from an infinite sheet of charge? There's a lot of ways to get it by. This is just one of many. Well, if we let A, which is the radial distance, go to infinity, then we have a plate that's infinitely large. Do y'all agree with that, class? What happens then? Well, just take a look. If we have, and this is an important point, by the way, if you have a surface of charge now, call this, try to draw it this way. So this is X, this is Y, and here's Z. And I'm saying I have a surface of charge, infinite surface of charge that has rho S on it, right? Well, it means that A is going to infinity. What happens over here when A goes to infinity? Can y'all see it? What happens to this term? A goes to infinity, we got Z over the square root of infinity squared plus Z, right? What is that? Zero. It goes to simply 1 or rho S over 2 epsilon naught AZ. And I have a comment about this. So we assume we were above here. So if we're above here, above this infinite surface, this has a surface charge density rho S, the electric field, if you're above it, is simply rho S over 2 epsilon naught AZ. It's always pointing away from a positive charge source. Y'all with me, class? How many see this? You'll notice it is not a function of Z. And that's because we have an infinite charge system, right? The way I always tell people how to think about this, if you have an infinite plate of charge and I'm up a given distance, say 10 meters, and I look at it, I look that way, I have to go out to 90 degrees with my head to see the horizon, 90 degrees that way, 90 degrees in every way to see the horizon. You go up 100 miles, still the same thing because it's infinite. The assumption is infinite. And because of that, the electric field will never change in its magnitude. However, if you're below it, it will change the direction. Now the electric field here, if you're below it, will be minus rho S over 2 epsilon naught AZ. It's always going to be pointing away from the positive charge. Do y'all follow me? How many see this right here? Now, in the book, he does this same kind of deal, only he uses an infinite line charge to get the differential electric field in the Z direction. And he integrates it over all possibilities and he gets the same result. Y'all follow me? It's easier this way, I think. But I wanted to do it this way because now we're going to do his problem. The one difference with his problem and this problem is the rho S value here is really some constant. It's, I don't know, 12 nanocoulombs or something times rho. Isn't that right, class, for that problem? All right. We're going to do the problem. Again, same exact thing as what I've just done. Only now, the form of this integral is going to change slightly. Y'all with me? Let me erase this over here and we'll do it. And I'm going to tell you one thing. Like, you can come up with the craziest kind of form for rho S. And you can get bizarre integrations that will drive you nuts. But that is not the focus of this class. It's to craft the integral so it can be solved if you need it. All right? That's the whole idea. In graduate school, well, I don't even know what they do anymore, but what they'll come up with, they won't have just like an actual plate like this. They'll have a deformed plate. They'll have the thing be like a conic section or basically a parabola, proloid spheroid thing, and they ask you. So you have to write these very, very detailed integration, differential electric fields, and then do the integration. They come out with all sorts of things like spherical Bessel functions and all these other things. But in essence, it's the same thing we're doing. We're just finding the differential electric field and then going ahead and solving it by doing the integration. And we're using what I call the building block approach because we know the electric field from an actual ring. So over here, now I'm going to say, I guess I can use this right here. You can see this. Can everybody follow me on this? How I got this right here? Right? That is the differential electric field right inside here for a loop with a thickness d rho. Now, the rho s value is different for that problem. I'm just going to say the rho s value for his problem is some constant. I'm going to use A times rho, and I think he does that in the book, but I'm not sure. A is just a constant. A is actually, is it 12 times 10 to the minus 9? Is that right? All right. He's saying it's 12 nanocoulombs per meter squared. It doesn't matter what it is. So over here, if you look at this, I'll write it down here. Now I have EZ equal. And might as well do it one time this way. So I have 12 nanocoulombs here, or I call it A. So A, replacing rho s with A rho, then it's D rho, then it's times Z, then it's times rho, AZ, over 2 epsilon naught, and Z squared plus rho squared to the 3/2 power. And here rho goes from 0 to A. A. Same exact things before. Y'all follow me? What's the big difference here? I got rho times rho. I got a rho squared on top. Y'all follow me? Let me write that over here. Now my EZ integration. I'll take out the constants. I have A, Z, AZ, unit vector, over 2 epsilon naught integration of rho equals 0 to rho equal A. And then I have rho squared d rho over rho squared plus z squared to the 3/2 power. Y'all follow me? And again, I'm replacing things. So that integration is the form of x squared over x squared plus a squared to the 3/2 power dx. Now that's an oddball integral. Does he have that in the back of the book, do you know? I looked this integration up. You can do it by parts, and I'm going to tell you, I think he does it by parts in his book. You can let u be equal to rho, therefore du is d rho, and then you can say, v or dv is equal to d rho. I'm sorry, is equal to minus 1 over rho squared plus z squared to the 1/2 power. And you can do the thing. That's equal to v. Then you take dv. But you get a udv thing. Basically it's integration by parts. Y'all follow me, class? You can do that, and I think he does that in the book. I won't ask you to do that. But the integration, I looked this thing up, and he has a solution in his book. I actually looked at both of them alpha to do this, so I thought I can do it by integration by parts. But I got asked this when I was coming in, so I figured this is integration by parts. It's going to take forever. When you do this, I'll just put down the solutions are there, right? For his thing, he's going to get this is one of those I have square root of x squared plus a squared over square root of a squared plus x squared times sinh to the minus 1 of x over a minus x. X is really equal to rho, and a is equal to z, but it's a pain in the butt to do this. I'm not going to ask you to do that integral, right? But I do. You have to be able to set it up. Now, if I was ever going to ask you to do an integral like this, I would give you integral tables. All right? I'm just leveling you. I'm not going to ask you to do something that bizarre. But it's a good problem to make you think to do it. And he does use integration by parts, doesn't he, for this one? You can do it with integration by parts, but it's kind of a long, drawn-out thing. Okay. That's that. Now, before I continue, any other questions? I got a couple things to cover today. We did the infinite plane, right? We did the ring of charge. We did the disk of charge. We did the infinite line of charge. Y'all follow me? we've checked the boxes for all the things. And anytime you have combinations, if you have an infinite line of charge and a point charge and an infinite sheet of charge, and you want the electric field at any point, you simply add the electric field from each one of those charged systems together. Do you all follow me? And that's it. At the point of observation. That's it. It's really linear systems, so you just add it up. And now today, I want to show you something that is sort of your salvation in a sense. It gets rid of a lot of the anguish of these differential integrations. Everything we've done so far to this point, we're calculating electric field. We have to find the electric field from a differential amount of charge, and then we have to integrate over that total charge system to get the total electric field at any point. So it's a differential, then a lot of integrations, and it can be a pain. But with Gauss's law, now how many remember Gauss's law? There's a differential form and an integral form. I'm going to give you both. Gauss's law says this. It says the integral of something called the D field that I'm going to get to in 1 second over a closed surface BS is equal to the charge enclosed. That's the integral form. The differential form is divergence of B is equal to the volume charge density. I'm just putting them down, I'll explain it. Now the D field is related to the E field. The D field is equal to epsilon times the E field. If you're in free space, in other words, a vacuum, then you have the D is equal to epsilon naught E. And epsilon naught is just a constant. It's based on nothing being there. And it's 8.854 times 10 to the minus 12 farads per meter, approximately. It's based on measurements. Y'all with me? Or 1 over 36 pi times 10 to the minus 9. Now, you can see one thing about this. This integrational form means nothing unless you put it in terms of an application. And here's where you can use Gauss's law. How many remember Gauss's law in physics? Gauss's law is one of those things that it saves you so much angst, so much reconsideration. But it can only be used when there's a high degree of symmetry and you can exploit the symmetry. The first thing I'm going to do is show you the easiest form of an application of Gauss's law to a problem. And you're going to have to understand this is something you have to be able to see before you can use Gauss's law. So if I have a point charge Q here, and I come out a radial distance R away, I'm going to make the statement that the electric field's magnitude here, or the D field, either one, will be the same at every distance R away, the magnitude. How many agree with me? Based on your understanding of electrostatics, it should be absolutely clear. That electric field is only going to be a function from the distance from the charge to the point of observation if we're worried about magnitude. That should be obvious. So now if I put a sphere around here, it's going to be a spherical surface of radius R. Y'all with me? Then I can say, well, if I wanted that D field without going back to the, basically to the most fundamental form, Coulomb's law, I can say, well, the integral of D dot ds over that surface is going to be the charge enclosed, which is Q. Now we can make this formal, and I will this time, but I won't from now on. I can say I have a differential surface here, ds, it's in spherical coordinates, right? If I have a differential surface here, technically it's equal to R d phi in spherical, right? Some of you don't remember spherical probably a little. You haven't had it in a while, you don't really recall it. So in spherical coordinates, this is the z, this is x, this is y. We superimpose the Cartesian Cartesian on here. And now if you have a distance r away, r is equal to the square root of x squared plus y squared plus z squared. It's just the distance from the origin, and I'm doing a comparison. Then when we take a look at a differential surface at a distance r, you're going to have one side is going to have r d theta. That's theta, that's when you're moving this way. Then you're going to have a surface where this becomes r sine theta d phi here. And this would be a differential surface at a constant r. It's in the book, and I pasted some stuff on OneNote to show you this. Y'all with me? So if we take a look at a differential surface on a differential spherical surface at a constant r, this differential surface becomes the distance r squared, in the book it's small r, times the sine of theta times the theta d phi. And it is in the AR direction. There is a sense to that, a vector sense. You can use a small r. Did you all follow me? How many remember that or saw it? I posted those things for a reason because they help you visualize what I'm talking about here. Now, if I take a look at this, I'm going to take this one, I'm going to say, I need an integral over the surface of d dot ds. Just work with this. The d field's going to be the same magnitude. So I'm just going to say it's d in the r direction, AR. I have to dot that into ds, which is going to be equal to r squared sine of theta d theta d phi, and that's equal to q, the charge enclosed, which is just q. All right, now we can do this, and please pay attention. Here's where people make mistakes left and right. All right. D theta is the first value, right? Theta is measured from the North Pole to the South Pole. It goes from 0 to 180 degrees or 0 to pi. Do y'all follow me, class? So when we do this, we can say theta goes from 0 to pi. Now, phi is in the xy plane. Think of the x-axis. Think about going west. You go all the way around, back until you hit west. So it boils from 0 to 2 pi. Y'all follow me? So for phi, it goes from 0 to 2 pi. And I didn't put this in here, but this is AR right there. Now, I'm just going to mention this just so you have completeness. We have a unit vector AR, it's dotted with AR, that's 1. Y'all follow me, class? AR dot AR is 1, we can get rid of it. Now, the next thing we do when we do this integral over here, you'll notice r squared, there's nothing that's a function of r over here. Is there, class? I can pull r squared out in front. Y'all agree? Now, I've got the outer integral phi. Nothing in here is a function of phi except d phi. When I integrate d phi, I get phi. Evaluated from 0 to 2 pi is just 2 pi. Do y'all agree? So I put 2 pi here. I have r squared times 2 pi. Now I have to integrate sine theta, which is minus cosine theta. Agree? And I have to evaluate that from 0 to pi. Well, you might as well, since it's minus cosine, make it cosine and go from pi to 0. Cosine is 0, is 1, minus the cosine of pi is minus 1, or 1, minus the minus 1 is 1, plus 1 is 2. So this is 2. Then you have dr here, and that's all equal to the charge enclosed, which is just q for this thing. And you can see now that the d field in the radial direction is simply q over 4 pi r squared in the AR direction, by the way. And that is the d field. Do y'all agree with that? What do I do if I want the e field? Now, I didn't do anything with the fundamental for using Coulomb's law, but what is the, if you wanted to know what the E field is, what do we need to do? Just divide it by epsilon, and you realize that that is the electric field from a point charge. It's simply Q over 4 pi epsilon r squared, right? Now that's a simple example. Now we're going to apply Gauss's law to things that are a little more complicated, but this is very important because you'll see how it makes life so much easier. We're going to start with the line charge, and then we'll do a fact fight. You'll see this. Now, if you've had Gauss's law, this might seem a little boring to you. You know it already. But there are going to be some examples you haven't seen that make it a little more, or make it a lot more useful. And again, I'm going to show you something. You know the result, but I'm going to show you an easy way to get it. Suppose I have an infinite line of charge right here on the z-axis, and it has a charge density rho L. All right. Now, what I'm going to do is create a Gaussian surface. First, I have to make a comment. If I come out a distance rho from there, from the axis, do you agree that the magnitude of the D field right here, the D field will be in the radial direction, right? And the magnitude will only be a function of the distance rho away. You have to be able to see this. Do y'all agree with that? Y'all with me, class? If it's an infinite line charge and I'm not at distance D, it doesn't matter what phi I'm at. Really, the D field's magnitude will be the same. Do y'all follow me? Now, what I do is create a Gaussian surface around this thing. So I'm going to do this first. I'm going to say that this is X right here, Y and Z. Then if I put a cylinder around here, and I'm going to make this, well, that's a loud cylinder, make that cylinder of a height. Anytime you have a choice of things, always go with one. So I'm going to say the height of this is 1 meter. All right. Now, here's the surface I'm talking about, the outer surface on the cylinder right here. And I need ds here. And ds here would be rho, d phi, dz, it would be in the a rho direction. Now this is important. You all see the D field's only radially outward, right? With me? So I'm assuming that the D field everywhere is going to be just D rho A rho. Now I write Gauss's law in the integral form, so I say the integral of d dot ds over the closed surface is q enclosed. You'll see this in a second. When I have d dot ds here, it's interesting. All right, technically, I have a surface at a constant radial distance rho, but I have the top and bottom surfaces too. Do you all see that? I have a top surface, it has to be a closed surface, in the bottom. But the thing is, the D field is in the radial direction. And when you take a look at the D field dot ds there, it's 0. That's the reason the top part and the bottom part you don't worry about. Because the surface here at the top, ds on the top or bottom, will be equal to, if you think about it, it's going to be d rho, that's a differential this way, and then it's going to be times rho d phi, but it would be in the az direction. Do y'all follow me on that, class? When you have az dot a rho, we assume that the D field, we can see it, it's going to be only radially, the dot product is 0. Do y'all follow me? How many understand that? Okay. If you, anybody not understand? Do you guys understand what I'm talking? Go ahead.
I was under the impression that electricity would travel on the sides.
What's that?
Electricity.
There's no electricity travel. The charge is only on the z-axis. This is the thing. The z-axis is where the charge is on. The D field is what we're trying to calculate. We can get D field once we have the D field. So with this one, if I take a look at this, the integration left on the outer edges would be an integral here. It's a double integral technically. And it's going to be the D field, the unknown D field that's in radial direction A rho. And it's dotted into ds. ds on the outer surface, right there, is going to be rho d phi times dz A rho. And I have to do this carefully. So phi goes from, now this is the xy plane, from 0 to 2 pi. And my height goes from 0 to h, right? What did I make h? 1. I'm allowed to make it anything. Make it the easiest number in the world. 1. So I go from 0 to 1 here. That's equal to the charge enclosed, right? How much charge is enclosed in this surface? It's just the amount of charge from 0 to h. Do y'all agree with that? That's the only thing. That's just h, or 1 times rho l. Y'all follow me? That's the reason I chose 1. So this becomes just rho l. Now, just work with me on this. I'm not trying to bore you, but I'm trying to be absolutely clear about how easy this stuff is. If you look at this, I put a rho here. A rho dot a rho is 1. I mean, do y'all follow me on this? Your dot product, anytime you have ax dot ax, a rho dot a rho, it's always 1. Now, if I had a rho dot az is 0, right? So if they're the same vector direction, if you have a rho dot a rho, az dot az, a phi dot a phi, it's 1. A phi dot az is 0. Anytime they're orthogonal, it's 0. So this gets rid of that. Rid of that. Now I have to do this integration. This becomes pretty obvious. What do I have? I have d phi from 0 to 2 pi is 2 pi, right? And then I have rho just comes out front. I have d rho here, and my dc integration is from 0 to 1 is equal to rho l, and you can see d rho is equal to rho l over 2 pi rho in the a rho direction. What's the E field going to be, class? E field is? That's it. Y'all see that? That's it. Now, you knew the answer to that one because I did it. But you realize we didn't do anything with a differential charge and do an integration. Here, it's a relatively trivial amount of work compared to the other way. Now we're going to apply this to some more things. All right? First, y'all with me so far? Now we're going to do some of the problems in the back. And I'm going to start with one. And this is kind of classic. Suppose if I have a sphere with a constant or with a charge density, and I want to know the actual value of the electric field or D field on a surface, but it's spherically symmetric. So follow me on this. This is going to be a sphere. And we're going to assume I have a sphere here. And let's see. And I'm just going to say the sphere has got a radius of A. And inside here, the sphere has a charge density, a volume charge density of, let's make it something that has to be spherically symmetric, so I'm going to make it simply R, and that would be coulombs per meter cubed. So this is a real simple one. Then you can make a capital R if you like. So it's got a volume charge density that's constant in there. And I want to know what the D field is versus actual radial distance. Y'all follow me, class? Sorry, it's not drawn the way you want, but let me just take a 2D slice of this. So if I have this, here's my sphere of radius A. And what I'm really asking for is at any given distance R away, or it could be smaller, what I want to know is what the D field is. So here's my surface. It's a surface here of a radius R, and I want to know, I'm going to apply Gauss's law to that, and I'm going to figure out what the D field is, and I'm going to find the E field. So first of all, if you think about this, if the charge density is only a function of radial distance away, do you all see, no matter how I look at that, at a given distance R away with respect to theta or phi, it looks the same. Everybody? Now, if that works, in the D field, you're going to have to at least be able to see this is always in the radial direction, just by arguments of symmetry. Y'all give me that? So now I come over here and I say, well, the integral B dot ds over the closed surface is the integral of, now this is going to be rho v dv. Okay? Now, follow me on this one. Some of you are unfamiliar with spherical coordinates. You're going to need to know these. And on the quiz on Wednesday, I'm going to give you problems that may cover both spherical and cylindrical coordinates. So you need to get up to speed with this stuff. You can't just let it be on the back burner. Over here, the integral of d field. Well, I don't know what the d field is, but I know it's in the radial direction. So I have b of r, it won't matter if it's a capital or small, AR here, dotted with the differential surface. This is spherical, it's on the outer constant origin. So this is going to be r squared sine of theta, and then it's going to be d theta d phi. As such, it's in the AR direction. It's a double integral. And here, see theta goes from 0 to pi, and phi goes from 0 to 2 pi. Here's where the actual, we're going to have to do a little work here. This is going to be a triple integral of the charge density, and I'll just call it small r here. Small r, and it's good, that's the charge density. What I can do is this. I can say it's rho 0, some constant, times r. So I'll make this rho 0, whatever that is, times r, times the differential volume. Differential volume is r squared sine theta d phi dr. And now I have to put the limits on this. Do y'all follow me? It's a differential volume in spherical coordinates. You've had this in physics and stuff. You may not have used it a lot, but you're going to have to get real familiar with it. Now we put the limits on here. Here, theta will go from 0 to 2, or 0 pi, pardon me, 0 pi. Phi will go from 0 to 2 pi, and dr will go from 0 to r, whatever the r distance is that we're at. So I'll go from 0 to r away. So you can, what I'm really saying is it doesn't have to go out to A. It can go to any point we can get this d field. Y'all follow me, class? We can go to A, but we go from here to A. That's as far as we can go on this side because there ain't no more charge density after that. Y'all follow me? I mean, it's 0 after that point. So if we do this, now I'm going to make mention of this. Just hear me. AR is 1, right? Y'all see what I'm really doing here? I'm getting the surface of a sphere, the area, and multiplying it by dr, right? How many know what the surface of a sphere is of a given distance r, the radius r? 4 pi r squared, remember that, all right? You're going to use that all the time. So this integration over here will become 4 pi, and I'll use capital R squared, and it's times dr. On the other side, now I have to do this integration, right? But you're going to notice something. Here, the d phi and d theta integrations there will just bring out 4 pi every single time. Y'all hear me on that? So the only integration you have to do is the dr. On this side, it's going to be 4 pi. And that takes care of phi and theta, period, always. Now here I have rho naught. And then I made this to be a function of r. So now I got r cubed dr, right? What is r cubed dr? Integrated, it's r to the 4th over 4, isn't it, class? So this becomes r to the 4th over 4. You can see the 4 pi cancels. And that would be, and then you can divide by r squared here, which means this is really going to be r squared on top, and that's good for 0 greater than r less than a. Once you get beyond a, you have to set a hard limit on this integral from 0 to a, and that'll be a finite amount of charge. I'm going to give you some problems with this. We'll talk more on Wednesday. You're going to get a quiz, and it's going to be related to the homework today and last time, all right? And it will be something, I'll give you the differential surfaces and volumes for cylindrical and Cartesian. You have to know, cylindrical and spherical, but you have to know what they are for Cartesian, all right? And it's going to be something related to the home. Everybody with me? Okay. Please don't try it. It gets a lot more crazy quick.